In this lesson, we're going to revisit solving exponential and more so logarithmic equations from the beginning of the course. We'll start with exponential equations, and then we'll move into logs and go from there. Let's see if I can rewrite any of these equations such that the we have the same exponential expression with the same base on each side, then the exponents will have to be equal. 243 happens to be 3 to the 5th power. Therefore, this tells me that x has got to be 5. Let's see, 4e to the 2z equals 16. Well, I'm going to start by getting this base by itself. I'm going to divide everything by 4. E to the 2z is equal to 4. What do I do from here? I don't know how to rewrite 4 as e. However, that doesn't need to stop me. I can undo this exponential by using its inverse, namely the natural log. So putting in natural log of both sides. The natural log of e to the 2z, log base e of e to some exponent, is just that exponent. And the price I pay is I have a natural log on the other side. Divide everything by 2. And I have z is equal to the natural log of 4 all divided by 2. Or maybe better yet, that's like 1/2 times the natural log of 4. Or how about that's the natural log of 4 to the 1/2 power, which is the natural log of 2. Let's see if we can try something here. How about we add 8 to both sides? And I get 5 times e to the x plus 2. And that's equal to 22. Dividing by 5. I get e to the x plus 2 is equal to 22/5. So let's see, I can get to the exponent up here. Same trick I used over here. I can use the inverse function of the exponential e, which is the natural log. Natural log of both sides. Log base e of e to some power is just that power. And that's just the natural log of 22/5. So x is equal to the natural log of 22/5 minus 2. Or maybe on my graphing calculator, I can get an approximate value for that. How about I get the natural log of 22/5 minus 2, which is about negative 0.518. E to the 2x minus e to the x minus 20 equals 0. Oh, this has the similar structure as like y squared minus y minus 20 equals 0. I think, as we saw at the outset of the course, we could factor this like y squared minus y is 20. This factors to be about y minus 5 and y plus 4. Or how about e to the x minus 5 and e to the x plus 4 equals 0. Which means the solutions to this equation are the solutions to e to the x minus 5 equals 0 and e to the x plus 4 equals 0. See, I can solve this first one. I add 5. If e to the x equals 5, then if I do natural log of both sides, then x is equal to the natural log of 5. Similarly, if I solve for this, I get e to the x equals minus 4. And I don't even need to type in natural log of negative 4 and get an error to know that it's not possible for a positive base to a power to be negative. So there's only one solution to this equation, and it's x is the natural log of 5. Similar structure to this, looks kind of like a factoring problem again. I'll turn this into a factoring problem. How about I 7e to the x minus 3 equals 0. Let's see, I need to break this apart. Let's see, how should I do that? I'm going to multiply the first and last. Negative 18 is the multiply, the add is plus 7. A pair of numbers that multiplies minus 18 but adds to 7. I think that's positive 9 and negative 2. Which tells me that I could split this middle term into plus 9e to the x's minus 2e to the x's minus 3. And then I could factor this by grouping or use a box. It doesn't matter. How about I'll practice factoring by grouping. I'll turn these subtractions to the plus negatives. I think what's in common between 6e to the 2x and 9e to the x is 3e to the x's, leaving with 2e to the x plus 3. I think a minus is in common. So factor by grouping, 2e to the x plus 3, and then 3e to the x minus 1 equals 0. So these are the common terms, and what's left over is there. So that tells me that 2e to the x plus 3 equals 0, or 3e to the x minus 1 equals 0. I can solve this. I get e to the x equals minus 3 halves, which is impossible. I get e to the x is equal to 1/3. So x is equal to the natural log of 1/3.